Now, typically we do digital logic, like our sum of products or product sums form uses OR gates, AND gates, and NOTs. But here we saw that we make our gates NANDs and NORs. And so we might think like, how do we get to our AND then? Well, we know that we're able to make a NAND, and we're able to make an inverter. And so if we just invert something twice, this equals just an AND gate. So that is the approach that we take. You might think that, hey, we can take some PMOS and put them at the bottom for 0, and then we've got a resistor here and a voltage and then ground. You could say that that will give us an AND function. Sorry, these should have been in series, so I guess this would be for making an OR. Either way, the problem is that the PMOS won't work connected to ground like this. They've always got to have one leg connected to the positive in order for them to work right. So this, it just won't work. It won't make an AND gate, or in this case, an OR gate. So this is the way it is done, right? We take a NAND and hook it to a NOT. So let's look at how we do this, right? What we're going to have is our NAND gate out of Nmos. So we've got these guys linked to ground, and then a resistor, and we've got, we'll just say, a plus this time, and we've got, we'll just say, A here and B here. And this is the output of our NAND gate. And then we know to make an inverter that we can throw another resistor here. And so we're going to throw that in. And then we're going to have our gate. Right, this is our NOT gate. And the output is going to connect to the input of this transistor. And then this is going to be our final output. So now let's just run through, I guess we might as well just run through all the cases real quick. Here, I'll label this. This is also a plus. So if we have, say, two zeros, that means that both of these guys are open. And so that means a 1 is flowing through here, and we know that this is an inverter. We know that a 1 means that this is closed, and so that means we're able to get a 0 on the output. So two zeros in, we get a 0 on the output. Now let's look at the case where we've got a 1. So it looks like this guy's closed, this guy's still open. So we have a 1 that flows through here. And so that means that this guy's closed, and we get a 0 on the output. And of course, you should know now that these are commutative. If I flip them around, we're still going to have the same result. But if they're both set to 1s, means this guy's closed. That means I now get a 0 here. And the 0 means that this is open. And so that means that we get a 1 in the output. And this is, in fact, acting as an AND gate. So now this should kind of lend a little bit of insight into the idea why we did the exercise at one point where we made everything out of NAND gates. because as it turns out, NAND gates they take up less space because they use less transistors. They're easier to manufacture, and so that's why we do most of our functions out of NAND gates, right? Because just a NAND, a 2-input NAND takes 2 transistors. An AND gate takes 3 transistors, or 50% more. And so 50% more, that can take up a lot of extra space if you're designing a chip or something along those lines. So this is how we do and you can kind of follow a similar process to get a bunch of other gates, and like ORs, and then exclusive ORs. You have to kind of break up how that function works, or there's a couple of tricks along the way that we'll look at later.